Hi, my name is Tony Song, and today I'll be presenting on optimizing machine learning compute in production with AWS SageMaker. For those that didn't get to read the abstract for this talk yet, I'll go ahead and read it. In the rapidly evolving landscape of machine learning, efficient resource management is crucial for optimizing performance and controlling costs. This talk will explore best practices and advanced strategies for optimizing machine learning compute in production environments using AWS SageMaker. We will delve into key features such as SageMaker's managed infrastructure, auto-scaling capabilities, and inference components. Attendees will gain insights into leveraging SageMaker's integrated tools for model monitoring and automated scaling to enhance model performance and operational efficiency. So a little about me before we dive in. I currently work as a senior machine learning engineer at Capital One on the Gen AI serving team. I live in Brooklyn, New York, and before Capital One, I worked at Nestle Purina as a machine learning engineer. And even before that, I worked in the medical devices industry at companies like Johnson & Johnson and Philips as an R&D and manufacturing engineer. I made the career switch into machine learning after I received my master's in data analytics. I also went to music school and moonlight as a jazz guitarist in the New York City area. I'd love to connect with you as well, so feel free to add me on LinkedIn. The objectives for today are to understand the basics of AWS SageMaker and how it's used in the context of LLMs, learn about the challenges in optimizing ML compute for large models, familiarize yourself with SageMaker features for serving ML models, learn how to set up a scaling policy with inference components, and learn about inference performance testing considerations and techniques. And for the agenda, we're going to go over an introduction to SageMaker, talk about ML infrastructure challenges, see how SageMaker auto-scaling and inference components can help us deal with some of these challenges, touch on performance testing in the context of LLMs, and then end with some Q&A. I'll kick off the talk with some interesting quotes that speak directly to the challenges of hosting LLMs. Both are from Jensen Huang, the CEO of NVIDIA. The demand for our GPUs is so high that we can't make enough of them. We're doing everything we can to increase supply, but it's a challenging situation. That quote was from 2021. Here's another one from 2024. Demand is so great that delivery of our components, our technology, infrastructure, and software is really emotional for people. You can tell from these quotes that there is a huge demand for high-performance computing solutions. And because of that demand, there is a lot of competing for these resources across many industries. We'll touch back on the challenges with obtaining GPUs, but first I'll go over a short intro to Amazon SageMaker. What is SageMaker? Amazon SageMaker is a fully managed machine learning service from Amazon Web Services that provides tools to build, train, and deploy models. We'll focus on the deploy part for this presentation. SageMaker interfaces closely with other AWS services like S3 to store model objects, CloudWatch to trigger alarms, and Lambda. You can see in the bottom right figure how some of these services interface with each other. SageMaker can get predictions, also known as inferences, from trained machine learning models using a broad selection of ML infrastructure and model deployment options. These include serverless GPUs, LLM support, deep learning containers, elastic container registry, and inference endpoints for hosting. For Kubernetes environments, we can also take advantage of open source AWS controllers for Kubernetes, or ACK, which lets you directly manage AWS services from Kubernetes. ACK makes it simple to build scalable and highly available Kubernetes applications that utilize AWS services. One of the big challenges for my team at Capital One has been to optimize our deployment costs. These costs are mainly due to the expensive hardware required to host large foundational models. Also, model-specific configuration needs and varying request rates lead to suboptimal hardware utilization. For example, if we need to have a model up and running that utilizes P4D instances, which are powered by A100 GPUs and are difficult to obtain, and the model doesn't receive any requests for an extended period of time, we are still paying for the provisioned instances. This also requires meticulous planning of on-demand versus reserved instances to optimize costs. There are many factors when considering optimizing inference, as you can see from the two figures shown on this slide. Ideally, we want to have high throughput, low latency, and large batch sizes with many concurrent requests. And on top of all that, we want to have low costs. The challenge is that throughput increases with batch size, and latency increases with higher throughput and longer input and output tokens. Also, higher input length reduces supportable batch size. Going more in depth with latency, We can measure model latency by adding the time to first token to the time per output token times the number of tokens generated. Total latency includes other factors, such as queue weight and tokenization time. One of the solutions to tackle some of these challenges is to use SageMaker autoscaling. By default, SageMaker model deployments do not have the ability to automatically scale instances up and down. SageMaker autoscaling dynamically adjusts the number of instances provisioned for a model in response to changes in your workload. For example, when your workload increases, autoscaling brings more instances online. And when your workload decreases, autoscaling removes unnecessary instances. You can see in the figure below how autoscaling works in the context of SageMaker, pulling instances from different availability zones as needed, then going through a load balancer to reach the endpoint. In order to use autoscaling, you need to define a scaling policy. The policy uses CloudWatch alarms to trigger instance scaling up and down. For example, a typical way to set up an autoscaling policy is to use target tracking, where you need a metric to track, such as model invocations per instance, and a target value, such as 60 invocations per instance per minute. And if CloudWatch detects those thresholds being hit, then instance scaling would be triggered. Other types of autoscaling include scheduled scaling, where you set the scaling based on a predetermined schedule, and step scaling, which is a more advanced configuration, where you specify how many instances to deploy under what conditions. For Kubernetes environments, there's also an ACK controller for application autoscaling. Other important parameters to define are the minimum and maximum number of instances, the scale-in cooldown period, which is the time after a scale-in activity completes before another scale-in activity can start, and the scale-out cooldown period, which is the time to wait for a previous scale-out activity to take effect. The purpose of the cooldown period is to protect against over- and underscaling. It lets your autoscaling group stabilize and prevent it from launching or terminating additional instances before the next scaling activity begins. Another solution to tackle deployment challenges is to use SageMaker inference components. Inference components are a recent addition to AWS SageMaker released in late 2023, which allows for model packing on a single instance or set of instances. This offers workload isolation, independent scaling, and intelligent traffic routing. By utilizing inference components, we can break away from the one-to-one mapping of model to endpoint and improve overall resource utilization, including cost. In addition, inference components also alleviate some operational burden, as we can manage fleets of instances rather than disparate models. In the right figure, you'll see an example of some Python code to create two inference components using a single endpoint. Some parameters you need to define are the inference component name, the endpoint name, the model variant name, and compute resource requirements, such as number of accelerator devices required, number of CPU cores required, and minimum memory in megabytes required. An ideal deployment would utilize both inference components and autoscaling to optimize resources. Model variants can be set up with autoscaling on their own inference component hosted together in an instance family. We can visualize this pattern in the right figure, where we have two inference components, one hosting Llama 3 8B and one hosting Mixtral 8x7B in a single P4D endpoint. In order to combine inference components and autoscaling, we need to take advantage of AWS Managed Instance Scaling. Performance testing LLMs is not trivial, but I'll provide a high-level summary of what goes on. Note that I'll be talking about performance testing from an inference standpoint, not about the accuracy nor the cost. So, performance tests for inference are essentially load tests and are used to identify failure points, eliminate contenders, and establish baselines. For example, I may use the results of a performance test on a specific model to provide an SLA for latency and throughput to users. Load tests target system stability, and we need to pick the right performance testing framework for our needs. Some common load testing tools include Grafana K6, Apache JMeter, and AWS's own FM Bench. We want to test for an extended runtime under load to simulate different traffic patterns. Some parameters to consider tuning and evaluating for your performance test include the inference serving framework. Some popular frameworks out there include Hugging Face Text Generation Inference, or TGI, and NVIDIA TensorRT LLM, the GPU instance type and configurations, and the optimal number of GPUs. Using the right amount of hardware resources is key to optimizing performance for different LLM hosting use cases. For example, tensor parallelism on 4 GPUs for a Llama 2 7dB model is actually more performant than on 8 GPUs in a P40 instance at lower request rates. In conclusion, I'll summarize the key points for this presentation. Optimizing inference performance is critical for production ML systems. The last thing you want is errors or unacceptable latency for the consumers of your system. Hardware is a huge bottleneck for improving performance. We talked at the beginning about the high demand and scarcity of high-performance GPUs. Everybody wants them, so it's likely you won't be allocated as many as you wish, even if you have the money. AWS SageMaker features like auto-scaling and inference components can significantly improve hardware utilization, and combining inference components and auto-scaling can make the most of your provisioned GPU instances. Since we're limited on GPUs, we might as well make the most of them. And finally, performance tests are critical for planning hardware configurations and analyzing trade-offs with users. Coming up with the right configuration for your use case needs is usually a cross-collaborative effort, as your organization probably has a limited amount of resources. Different teams are competing for these resources for their foundation model use case, and there needs to be trade-off discussions for acceptable latency and throughput metrics. We covered a lot today, so thank you so much for your attention and time. We'll take the rest of this time for any questions.